Hello everyone. So waited 10 minutes. So far no student has joined, so I'll just continue. And as usual, the lectures will be available for anyone to view. So this is, so in the previous week, we had covered closed queuing networks and problems related to that. So this is the third last lecture in the series, third last session that I'm taking in the series. And today we'll be covering the content of week 10, which is semi-Markov processes. So as I usually do, I've been mentioning that while I was fairly familiar with the course, some of the topics I was only familiar with and not didn't really have a detailed knowledge about. So for semi-Markov processes as well, I had to study. So I went through the lectures by myself and I prepared notes. And these notes will be made available on the drive link. So we just browse through the notes for a bit. So we'll be solving problems on each of these topics. So firstly, we have Markov renewal processes. So we have these processes that happen at certain time intervals, and so then it's essentially the same process, repeating one after the other, and it's kind of happening in cycles. So these are renewal processes, and then we have, for renewal processes, we have excess time and spent time. For each renewal cycle, both of these quantities can be analyzed. And then there is this notion of lattice and non-lattice renewal processes, where in non-lattice it is fairly continuous, and in lattice the time, there is a certain periodicity in the renewal process. And then we have regenerative processes, which are one kind of renewal process. And so this is when the exact replica of processes are generated at various times. And the theory of regenerative process finds use in queuing theory, which we studied earlier. And then from renewal processes, we go to semi-Markov processes. And semi-Markov processes are, as discussed in the lecture, they are a slightly more generalized version of continuous time Markov chains. And then we use these notions to develop the theory for the MG1 queues, which are semi-Markov processes in a way, because the arrivals are Markovian and the departures are not. They can have any general distribution. So that's broadly what we are covering in this tutorial session. And so for MG1 processes, we have two important formulas. We have the mean formulas for Polat and Krishnik, or PK mean formulas, and we have the PK formula, or the PK transform formula, as it is known, which is the Z transform equivalent, from where you can actually derive all of the mean formulas. Z transform of all of the, or the probability generating function, PGF, of all of the state probabilities. So with that, let's start solving some questions. Okay. So the first question is kind of like true and false. CTMC, continuous time Markov chain, is general form for Semi-Markov process. So for this, the answer is no. So false, because it's actually the opposite. The Semi-Markov process is a generalization of the continuous time Markov theme, because in Semi-Markov process, the sojourn time, the time you stay in a particular state, is not necessarily exponential, but it's a finite time. So then that is what differentiates it from CTMC. So it has, so it is like so instead the CTMC is actually a special case of Semi-Markov. So this statement is not true. The second question is so let's first talk about renewal processes. So we have a renewal process defined by something xn, n equal to 1 to so on, right? This is a renewal process. Renewal process. And this has a this is distributed as f of t. So this is the PDF, right? And f of t. So we are also given that the Laplace transform of f of t is f of s, f bar of s, and then. So what you're asked to find out is the Laplace transform of m of t. So so what is m of? So m of t is a renewal function, right? So let's recall the theory a little bit. So we have these renewal intervals of the process starting again, and then so f, and we know this renewal process is it has a PDF of f, and so if you want to find out the renewal function, that is m of t, which is expected number of renewals in a certain time t, then we have to, then from the theory, we can see that it comes out to be sum of f n times convolution of f of t, which is the CDF of which is the CDF of this distribution. So so again, let's write down. So m of t is nothing but summation n equal to 1 to infinity f n star of t, right? And so this is n times convolution of so f n star of t. This is nothing but second. Just trying to revise the theory over here. So it is nothing but integrating f of So if you see f the probability Sn less or equal to S, this is nothing but integrating the n-fold convolution. So that's how it is derived. Integrating and obtaining an n-fold convolution, right? So here, so if we convert, you have to first remember that this is an integration from something like 0 to t f n star of some tau, v tau, right? And so by the integral properties, if we take the Laplace transform on both sides, by the integral property and the distributive property over addition, we'll have something like summation n equal to 1 to infinity 1 by s times Laplace transform of f n star t, right? And then by the property of Laplace transforms, this will come out to be taking 1 by s outside. This will come out to be f bar s whole to the power n, right? Because it's an n-time convolution, so it will just get multiplied. And then if we use the property for a geometric series, so then we will get this result. The Laplace transform of this function will be nothing but 1 by s, the first term divided by 1 minus common ratio, right? So this is how it is derived. So for Laplace, so this for this first result, so Laplace transform over an integral of some f of t dt is usually given by f of s divided by s. That's the formula for integral, and then yeah, the rest is just mathematics. So and this is the idea, and so similarly now you can just use this formula for various purposes, right? So let's say if let's say xn is distributed by this PDF whose Laplace transform is something like lambda by s plus lambda, right? Which implies, so and you have to find out Laplace transform of m of t. And you can directly use the formula now. So it's 1 by lambda by plus lambda divided by 1 minus lambda by s plus lambda. And so this gives us Laplace transform of m of t is equal to, so it's by lambda gets cancelled. So I think it comes out to be lambda by s squared eventually. So then and then so we know the Laplace transform of s squared, and the question is to find m of t. We actually want to find out the renewal function, right? So we can kind of check Laplace transform properties and try to invert it, and so what we'll get is So we remember if the Laplace transform is a constant, then the m of t, so the Laplace transform is 1. Remember what is the Laplace transform of m of t is nothing but to the power minus lambda s m of t. So if the Laplace transform is a constant, that means so we can apply inverse Laplace transform. So it's 1 by s squared. So m of t has to be of the form of lambda times double integral over some function of t, right? Some function of t. And so we need to find out what is the inverse of, so what is the inverse Laplace transform of a constant value, right? So that is what we need to find out. So for the unit impulse, and so the answer is actually, so for a constant value, the inverse Laplace transform is actually u of t, which is this function is nothing but 1 when t is greater or equal to 0, 0 when t less than 0. Or actually it's 1 when t greater than 0, and half for equal to 0 and 0 for t less than 0. That's how the function works. And then this inverse actually becomes 1 dot x. Okay. It's a lambda times the double integral of u of t dt. So that's so we should put it like t comma t prime dt dt prime. It's somewhat like that. I hope this makes sense. You can, of course, double check this inverse transform. It's not very confident about this, but okay, let's move on. And think I think I made a mistake over here. So the Laplace transform for t to the power n is 1 by s to the power n plus 1. So the answer for this actually is m of t equal to lambda times t. As simple as that. Lambda is a scalar. So yes, this will be the answer, which I think should also be obtained by the other approach that I showed. But let's move on. And so this is about, these are problems about renewal processes. Now we'll do some problems about problem number 3. We'll do some processes and do a problem about MG1 queues, right? We'll do a few problems about MG1 queues. So let's see. So let's say we have a system where some kind of queue, where arrival is so arrivals are the process. Arrival rate is something like 0.9 per second. So this is like arrival rate. So this is 1 time per second. That's arrival rate. And so one example of this can be like, let's say, service operations in CPU, right? And so the service time, so this and the arrival process is Poisson. The arrival process is going to be Poisson, and the service rate, the service process is 1 per second, and this is going to be deterministic, and this is going to be a constant value, so it doesn't change. That is no distribution here. So the question is, how do we find what should be the steady state distribution of number of requests that are lined up in the node, number of requests arriving in, number of requests queued up in the node, pi of z. That's what we know as pi of z, right? So firstly, we need to identify this as an MD1 queue. It's deterministic. The service is deterministic, and so it can be considered as an MG1 queue, or I should actually also write it as a Semi-Markov process. So then let's revise the theory a little. And for MG1Q, for the transform formula, we have to, so we have Ki is the probability that there are I arrivals during service, right? So then this probability is given by probability that the number of arrivals during service is I at, so given that the service time is T, and then again averaging over the distribution of service time. So let's find out. And the reason we need to find that is because we can kind of plug K of Z directly into the formula, PK transform formula, and get the PK transform. So let's do that. So Ki is equal to integral over time t equal to 0 to infinity, let's say. Probability that number of arrivals is equal to I, that is Poisson, right? So lambda to the power I by n factorial, a to the power minus lambda t. And then we have the service distribution, which is the service time is 1 per second. So then that is the service time, right? The service time is delta of t minus 1 dt, right? Because it's a delta function, so it's a delta function. it can only take the value 1. So what we'll do is it will just pick the corresponding value from here. Right, so it will be, and we know that lambda is equal to 0.1. So we can substitute it here, actually, the value of lambda. And then, so we get ki equal to e to the power minus 0.9. So we'll just pick the value at t equal to 1 according to properties of delta function. 0.9 whole to the power I divided by I factorial. So this will be the value of ki. And so the PDF is kz, which is nothing but summation over ki z to the power I equal to 0 to infinity, which implies kz equal to ki, so e to the power minus 0.9 as a constant, and then we'll have I equal to 0 to infinity, 0.9 times z whole to the power I, because e to the power I and 0.9 to the power I just multiplied, and then we have I factorial. And so this sum is e to the power 0.9z. So what we get finally is e to the power minus 0.9 times 1 minus z. Right? And so from the transform formula, we can check the theory again. We get this formula, right? 1 minus rho times 1 minus z times kz upon kz minus z. So let's do that. And well, we know the value of rho. Rho is nothing but lambda over mu. Oh, okay, so the service rate is 1 per second, which means that the service time distribution is delta of t minus 1, as I argued here, because t can only take the value of 1 second. And so, what is the value of rho? Rho is lambda divided by mu, which is 0.9. And so, so what we have is 1 minus rho, 1 minus z, kz divided by kz minus z. 1 minus rho is 0.1, 1 minus z, e to the power minus 0.9, 1 minus z, z divided by e to the power minus 0.9, 1 minus z. Minus, right? So this is the PDF. I hope this is understandable. So this was based on the this is the PK transform formula. And now let's solve another problem based on the mean formula for PK. So these are relatively simple problems. So let us, we need one, we'll focus on the, so these are the PK mean formulas summarized in this table, expressed in various different forms. So it's important to take a note of these formulas. And okay, so let's solve the problem. I'll return after a short break. Um, just want to give receive some student points.
Okay, I'm back. So let's solve a few problems for the PK mean formula. So just right. So we'll solve problems for PK mean formula. And so let's say you have a bank. Uh, bank, you have let's say some arrival rate customers arrive, and the arrival rate is lambda. So it's going on. horizon with the main lambda, and then the value of lambda is something like 30 customers per hour, right? And so, and then there are two kinds of customers. So we need two types of customers. So type 1, new the service time is for the type 1 customers is, let's say, something like service time is something like 20 seconds fixed, right? And or 30 seconds fixed, right? And for type 2, so the service time is kind of exponentially distributed with mean period of exponentially distributed with the mean service time 30 seconds, right? And so that is kind of the problem. So you have two kinds of customers with the same mean service time, but then they are very different in the nature. Right? One is a fixed, the other one is exponential. And so how do you really solve for this kind of a thing? So the thing which you want to calculate is the mean waiting time in the queue. And so we'll have to use, so this is clearly a general type of distribution. It doesn't follow one properly. So we'll have to use the theory for MG1 queues and the PK formulas for MG1 queues. So let us find out first the so we have the arrival process, right? The arrival process is clearly 30 customers per hour or half customers per minute, right? And we have two types of customers. So I can actually we have two types of customers. So for the first type, we have so we want to find expected value of S first, right? Expected value of service. So this will be, and then and we also should mention the proportion of the types of customers. Let's say this is let's say 60% of the customers, and this is 40%. So this will be the service time will be 60 by 100 times S1. 60 by 100 times expected value of S1 plus 40 by 100 times expected value of S2, right? And so then this works out to now S1 is deterministic and S2 also we know the mean. So 30 seconds. So then since we're seeing 2 units of minutes, so this will be 60 by 100 times 30 seconds, which is half a minute, plus 40 by 100 times 30 seconds, this is half a minute again. And this works out to be 30 plus 20 is 50 by 100 or 0.5 minutes, right? So a half minute for this. And then we also need to find accepted value of s squared, which is 60 by 100 times accepted value of s1 squared plus 40 by 100 times expected value of s2 squared. So S1 is deterministic, so we know exactly the value. So this is nothing but 30 seconds or half a minute. So squared plus 40 by 100 times so the mean for usually the variance for an exponential variable, you can check it out because S2 is exponential, right? So the variance is nothing but 1 by lambda squared again. So the mean so it comes out to be 1/4. I believe my calculation is right. 1/4 squared. Um, so that's the answer, and so that's kind of expected value. So it's squared. And then we want to find out the value for rho as well, which is lambda of rho. Lambda times expected value of the service time. So that's something like 1/4. Something like half times half 4. So the mean waiting time WQ is lambda times expected value of s squared by 2 times 1 minus rho. We can check it on the list formula here. This is the second formula in the list. And so this boils down to be half times 1/4 divided by 2 times 1 minus rho, which is 3 by 4. And so this comes out to be 1 by 12 per minute. 1 by 12 minutes. It's something like 5 seconds actually. Let's see waiting time of 3. So this is how we can calculate these quantities. Okay. And so but we sometimes might be provided other values, right? So let's say in another situation, the link, so let's say we have a network where there is a link and link utilization in terms of the maximum capacity is, let's say, 80%. and the service time for a packet or like to be delivered from one end to the other. So let's say accepted level of the service time for the packet to be delivered. So packet delivered over the link, the service time is something like 10 seconds. And standard deviation. The standard deviation is a sigma square equal to something like 5 seconds. Right? 5 seconds square or 5 seconds. Standard deviation is 5 seconds. And so what we need to find out is delay in Q, WQ, right? We want to find out the delay or delay in routing or service. This is important to find out. So let us see what are the values that we have. We have been provided rho equal to rho equal to 0.8, right? And rho is nothing but lambda times expected value of S. And so expected value of S is 10 seconds. So lambda is equal to 0.08 per second. And WQ, so WQ is nothing. Now we can check the mean value formula again. So it is lambda square. So if we take lambda in the denominator, it will be lambda square sigma square plus rho square by 2 lambda on the square. So that's the formula we use. We have our things that we need 0.08 square 5 square plus rho square is 0.8 whole squared divided by 2 times 0.2 times lambda, which is 0.08 times 1 minus 0.8. This also will come into this sentence. So you can do this calculation. I'll quickly pull out my calculator. As I usually mentioned, I just made up these values, so I'm not sure the correct answer. But let's see. The answer comes out to be 82.5 seconds or 1.375 minutes. You can double check. And so that's the answer. So let's see. So now as a follow-up, now let's say we make some improvements. So let's say after improvements, we have managed to bring down the service time to 5 seconds and plus minus sigma equal to, let's say, 2 seconds, right? So we reduce both the mean and the variance. And so now we want to find the waiting time, the value new waiting time, right? So everything else is the same. So lambda, the arrival rate is the same. It was 0.08 per second. And so should write distance expected value service mean, right? So again using, and then this is sigma minus. So again using the formula which you know equal to lambda square sigma mu sigma mu whole squared squared plus the rho squared divided by 2 lambda 1 minus 4. And also we need to find out the new value of rho, which will be lambda times its new value of service, right? And which means the new value of rho is 0.08 times 5. This also needs to be rho mu whole squared. And this will be 1 minus rho mu. So 0.08 times 5, which is 0.4 seconds. Sorry, 0.4. The rho is dimension respected. And so let's plug in the values and we get the new waiting time to be 0.08 squared times 0. So to be 2 squared plus little one here, which is 0.4 squared divided by 2 times lambda, which is 0.08 times 1 minus. And so one thing to note here is the rho here is half of the rho. As a rho old rho was 0.8, now it's 0.4. So this is a 50% drop in the link utilization. So let's see what's the drop in the waiting time. So to compute this value, so I'll again put out my calculator. Let's see. This comes out to be roughly 1 point. The calculation comes out to be 1.93 seconds. So this is a very, very sharp property. It's almost like it's almost like 1/20th. It's 82.1. This is like 2 seconds. It's almost like 1/40. And it's a double equivalent. So this just illustrates how crucial controlling the service time is. So you get a 50% drop in the link utilization and of course, a very high percentage drop, almost like 99.75, 99.75% drop for Metron. Not 90%, or 97.4%. This is a huge drop in the waiting times of the kids. And so another type of question is where you have to juggle with the formulas a lot. So let's say you are asked if the steady state waiting time is mu squared something like sigma squared plus sigma squared plus 1 divided by 2 rho by 1. So is this. So the question is true or false. So the answer is false. Because we have one formula which is rho squared by lambda plus lambda times sigma b squared. So this is squared divided by 2 times 1 minus 1. And so if we take lambda down here and do a little bit of exactly what we get is lambda squared sigma b squared plus rho squared by 2 times lambda times 1 minus 1. And so rho is nothing but lambda by b, right? And so it's not acting. Like so this is one, and you can take rho by 1 minus 2 as common. So 1 minus 2 comes out. We are looking at this lambda by 2 sigma b squared plus rho by 2 lambda. And so if we take 2 common, so if we have this. So this is what we have. This form clearly doesn't match what's shown here, because if we replace here rho by lambda by mu, so we get something like this. And I don't think there's any way these forms can be matched. So this is false. This was just a formula that I put up. So it's so so that's all I had to cover for this week. And I will prepare the notes and upload them. And also this video will be available on my YouTube channel. I'll hang around for 5 more minutes until in case any student joins.
Okay, I've uploaded my lecture, my today's discussion notes on the Drive link. I'll end the recording now and you can review it at your convenience. Thank you.